Hi, Alan Stratton from As Wood Turns. Those of you who have watched my videos for some time know that I'm a fan of jigs and fixtures and stuff that help make wood turning easier and more repeatable. But there is one notable exception to the list of jigs and fixtures available, and that's one that I don't like and that I think should be reserved for somebody that really has to do hundreds and hundreds of the same thing, and that is a jig to cut a sphere. They look pretty neat, but they really only take you so far, and then, in the worst case, is they limit your vision to what else you can do with a sphere. So I've decided to, in this video, to do a basics how to turn a sphere using a very versatile method that you can then refer back to as we go on and make maybe other videos that will derive from the same process or a sphere process in some way, shape, or form. Actually, I invite you to add to the list of potential videos of what else can you do with a sphere other than what I've thought of and that I'll publish. So, for now, let's turn a sphere out of some beech wood. Our objective is to turn a perfect sphere. And unless you have lots and lots of experience in turning spheres, it may be difficult to turn a perfect sphere. You may be tempted, as I was, to purchase a sphere jig. However, beyond the cost, a sphere jig still leaves you with a lot of cleanup. Let us start with a bit of sphere theory. Since a lathe's job is to rotate a 2D shape into a 3D shape, we will start with a circle. The key observation we need is the diameter measurement denoted here as D. However, as wood turners, we start with chunks of wood, preferably rectangular. We need a piece of wood that will include the circle and mount it as a spindle. While its length can be longer than the diameter, the other base dimensions are at least the diameter. To start, let's chop off the corners of the square to make a new regular polygon, or more specifically, an octagon. A regular octagon has 8 sides that are equal. According to mathematicians, and to help us move along, the length of each side of the octagon is 0.414 times the diameter. Yes, there are 8 sides, but we only need to use our calculator once. It is great to know the length of the side, but we need to know where the octagon side is relative to the square of wood. To make this math short, the distance from the square's corner to the octagon's corner is 0.293 times the diameter. By the way, it is the same from the opposite end of the square. This will help immensely to clip off the corners at the right spots and yields an octagon. But wait, it is not a circle yet. Since we have our circle mounted on a lathe, let us take a moment to mark the middle of each side of the octagon. There's no math here, just mark the approximate center. Note that on each end, the spindle axis already marks the middle. While we are marking centers, let's split each half side again in half. Approximately will do. We'll perfect the sphere later. Pick a tool and cut off each corner. That is, from blue line to blue line in this diagram. With these corners also cut off, we technically have a hexadecagon, another regular polygon. Despite the fancy name, it still contains our circle or sphere. We need only to round off the remaining corners. However, since we are turning from a block of wood between centers, we still have residual nubs at the centers, messing up our sphere. We have almost completed our sphere. In practice, it is still a bit rough, including the nubs at the turning axis. Once we remove the nubs and clean up the roughness, we will have our sphere. We'll cover the cleanup a bit later. We have completed our theoretical discussion of turning a sphere. Now let us switch from theory to the actual practice of turning a perfect sphere. This is a piece of peach branch still with the bark intact. It is mounted between centers. There is not much theory to taking a bowl gouge or a spindle roughing gouge to tool off the bark to yield a cylinder.
We can measure the diameter, but be sure that the spindle is longer than the diameter. If the cylinder is not perfect, use the smallest diameter since we cannot add wood back to the spindle. Any lesser diameter would nick. While there are alternatives, I will illustrate a safe approach. To be safe, I estimate where the sphere will be in the wood and mark one end of the square that will contain the circle. Then part at this line and waste off the wood beyond the mark. It is important to make the parting cut perpendicular to the side. And if I am to err, I must not cut into the square. If there is to be an error, let the square be a little fat. I waste off the wood, leaving a nub strong enough to continue the turning process. Please note that the length of the square has not been laid out yet. This is part of the safe approach I promised, since I'm delaying this measure until the first side has been cut, in case I need to adjust that top first side. But now I need to measure for the opposite side and make a similar cut to what I just did. Again, be sure not to overcut into the sphere or square. It is better to leave it slightly too large than slightly too small. Relating this back to the theory discussion, we have our square that contains our circle. But we do not have any concrete idea where the octagon actually lies. Out comes the calculator, pre-installed on every smartphone to perform two calculations. The octagon side is 0.414 times the diameter. The other measure is the distance between the square's corner and the octagon's corner. This is the same for both ends of the square. This is 0.293 times the diameter. I use the wood as my notepad to record the results of my calculations. I first mark circles on both ends. Their diameter is the length of the octagon's side. This uses the first measure. Then I shift to the side of the cylinder. Where is the actual octagon side? We know the length, but where is it on the side? This is where the second measure is critical. Whatever calculation results, I mark one corner from one end and mark the same distance from the other end. I check by confirming that the distance between these two marks matches the octagon side. Back to work at the lathe, I need to cut from the mark on the end to the mark on the side that will form another octagon side. This is at a 45-degree angle, but in practice I start at the corner and gradually cut back with the new corners approaching the marks. If I keep the distance to the marks equal on each side, I will get my 45-degree angled side. Repeat on the opposite end. Don't overcut. Have I said that before? It still applies, but does not make the project firewood. How about this? It looks like an octagon in the round. Remember those marks I made to divide the sides, the red lines, and again divide the sides of the blue lines? It's time to make these marks. I do not measure for these marks. Approximate is close enough for now. Now to cut the corners from the blue line to form the hexadecagon. Again, it is better to leave the wood slightly big than to be cut slightly small. If cut slightly small, the finished sphere will have to be correspondingly smaller. But if I cut too much, this will be fixed later. Now to round off the sphere by eye. We have been fairly precise up till now. This process to roughly round the sphere is a contradiction. Again, I warn against overcutting at this point. Still better to leave it slightly large. There's no need for perfection yet. There are many techniques to perfect the sphere, but I believe these techniques to be too much work for too little gain, except for the technique that I will show you next. By the way, the nubs at the axis are still there. Remove them as safely and as easily as you can.
So let's see where we are in the process. We've used an octagon methodology to approximate a sphere, but there's one big problem with that and some other smaller problems. The big problem is that we have a drive nub and a live center nub on this. Even if you had used a sphere jig to get to this point, you would have one of those nasty nubs or tenons from those processes. But we've gotten even closer with the octagon methodology. But now we'll take it and go another step further, because we've got to get rid of those first and then refine it second. So we're going to take it, if this was our original axis, we're going to take it and turn it 90 degrees. That will put these nubs in line of the turning axis so that we can remove them. And then, since generally speaking we'll probably have changed the diameter here relative to that, we're going to change it one more time and move it over to here to 90 degrees to that, so that any bumps there get turned away. And then as they've gotten smaller, I'm going to turn it 90 degrees again and refine it. So technically speaking, this is an X, Y, and a Z axis. So you start with one, you're turning it 90 degrees to go to the other one, and then you're turning it to the other 90 degree axis to go to the Z axis. In practice, the X and the Y are relatively easy to find. The Z that is relative to those is harder to find because you're removing all your marks. But then we're going to do the same process with sandpaper. And I recommend that you use 80 grit sandpaper in each case. We're going to take it, and on the first holding, we're going to use 80 grit and refine this area here. We're going to move it 90 degrees to that. Sandpaper again in this area to make it smooth in there. And then we're going to use it, turn it 90 degrees to that and refine it there. Now that's 80 grit. We still have other grits to do. For each one of those, we're going to turn it, have 3 rotations at 90 degrees to get it smaller and smaller, because we've got to remove the scratches from the 80 grit. So don't start with anything finer than 80, because you're just wasting your time. So let's continue with the reality of turning the sphere now.
I use several accessories for the sphere perfection process. At the bottom right is a cup faceplate. This one is threaded 1 1/4 by 8 TPI to match the lathe spindle. At top right is another cup faceplate. This is for the live center. I like the small cup since I do not need a big cup on both sides. It is threaded 1 by 8 TPI to go on the live tailstock chuck adapter at bottom left, which I find very handy for many projects. At top left is an adapter between 1 1/4 8 TPI and 1 by 8 TPI, since most of my repertoire of faceplates are threaded for 1 1/4 by 8 TPI. You can use whatever works for you. There are many alternatives. Back to work, the sphere is still a bit rough and needs to be more smooth and regular. This is done in 2 phases, each with multiple rotations. The sphere is mounted between the cup centers so that the original equator now runs north-south between the cup centers. It helps to have marked the equator. With a bowl gouge in a shear cut action, I work down the high spots, but do my best to leave the equator line. This mount is complicated by the remaining nubs from the previous mount. Once the ghost is minimized, I can draw my new equator line and shift the axis 90 degrees for the next axis. Same process now, but the nubs are gone. However, my sphere may be slightly football-shaped from the previous process. Now it's time to remove the slight points that generate the new horizon ghost. A shear cut is handled down and cutting edge near vertical relative to the spinning wood. Again, a new equator and shift the axis to the third possibility. The ghost should be much smaller now. I just do not want to overcut. My next tool choice would be a scraper. I watch the ghost at the top horizon of the sphere, hoping to make it disappear. While I want to take off all the high spots, I also want to avoid overcutting. Since I do not expect perfection at this pass, At this point, the tool work may be finished. However, if the sphere is too rough, possibly from being overcut, I can continue to rotate 90 degrees successively until I'm happy. With practice, that would not happen often. For the next phase, I shift to 80 grit sandpaper. This is essentially the same technique as with the tools. I prefer short strips of sandpaper held by my fingers at the ends. As the sandpaper curves around the sphere, the coarse grit removes any remaining high spots while still conforming to the curve. As before, the sphere may become slightly, very slightly, footballish. A 90-degree axis shift puts the points back into the sanding path. Another 90-degree shift finishes the smoothing operation for this grit. Now shift to 100 grit sandpaper and do the same sanding process again with the same 3 axis shifts. As the sphere is now regular and smooth, this is only to remove the 80 grit scratches. Next shift to 180 grit sandpaper and again sand the sphere. Again. This is only to remove the 120 grit scratches. Next shift to 240 grit sandpaper and again sand the sphere. Again. This is only to remove the 180 grit scratches. Next shift to 320 grit sandpaper and, guess what? Again sand the sphere. Again. This is only to remove the 240 grit scratches. Finally, shift to 400 grit sandpaper and again sand the sphere. Again. This is only to remove the 320 grit sandpapers. I'm finishing this sphere with my mix of mineral oil and beeswax. This is my utility finish of 1 pint mineral oil to 1/4 pound beeswax melted together in the heat of my attic. Do not do this on a stove due to the extreme risk of fire unless using a double boiler. Again, 3 rotations to apply and polish.
Now that you've made a sphere, the future is bright because we'll now take this and take various permutations and derivatives of the sphere process to actually do something much more, well, actually, I think this one's pretty as is, so we'll leave this one alone.